We will now do some exercises. So that we understand what we have learnt so far. So, 1, let T belong to d prime of R. So, T is a distribution defined on R such that T dash belongs to E of R. Recall E means C infinity functions. So, the distribution derivative of T is given by a C infinity function. Okay. So, show that T itself belongs to E of R. So, that means T is generated by a C infinity function. Okay. So, solution. So, let T dash equal to Tf, where f belongs to C infinity of R, which is of course E of R. Okay. So, define h of x equal to integral 0 to x f of t dt. This is to be appropriately interpreted when x is less than 0. So, it will be from x to 0. Okay. So, it is indefinite integral defined for all x. So, this has to be appropriately interpreted. Okay. So, this implies, so h dash is f and this is in fact h is a C infinity function itself. Okay, and you have h dash equal to f. Okay, and also if h is since it is an absolutely continuous function, in fact it is a C infinity function, and therefore it generates a distribution. It is locally integrable, so it generates a distribution, and you will have th dash is the same as tf, because h dash a classical derivative and the distribution derivative coincide. Therefore, you have t minus th dash equal to 0, and this implies that t minus th equal to c. That means we have to show it is a constant. That means that is equal to some t given by c. So, t is equal to t of h plus tc, which is t of c plus h. Okay. And therefore, if you write g equal to c plus h, what is g of x? G of x is equal to c plus integral 0 to x f t dt. And this itself is again a C infinity function. Therefore, t equals tg, g is in E of R, that is t belongs to E of R. So, if you have a differential equation dt by dx equals a C infinity function, then the distribution itself t will be a C infinity function. So, it will also be the classical derivative in this case. Okay. 2. Find all solutions t in d prime of R such that t dash plus at equal to 0, where a belongs to R. Let us say a positive. Okay, it does not matter, a can be anything. Okay, so we are looking at now at a differential equation, and differential equation we are looking for solutions in the class of distribution. So, these are called distribution solutions of the differential equation. So, we want to know what are all the distribution solutions which can be. Okay, so now consider, so solution. So we do exactly as we do in the classical case. This is a linear differential equation. What do? You multiply by the integrating factor. So let us consider t e power ax into t. So this you know what it means, because you are multiplying t by a c infinity function in the front. Okay, so let us take e power ax t dash. Then we saw that this satisfies the usual product rule. So you will get e power ax times t dash plus a e power ax times t. Okay, so that's equal to e power ax into t dash plus at, but t is a distribution solution of this equation, and therefore that's equal to 0. So you have the derivative, distribution derivative of something equal to 0. So then we know that e power ax t equals a constant. Again recall that we mean that this is generated by the constant function. So then this implies that t equals e power minus ax times c, or the equal to, or c e power minus ax to be, since we write. Okay, so now what does this mean? That means that is t of phi equals c times integral e power minus ax times phi of x dx over r for all phi in d of r. This is what we mean. So these are all, there is only one solution, that is in fact the distribution generated by the classical solution of this differential equation. Okay. So now 3, define for all phi in d of r t of phi equals integral over r mod sin x times phi dashed x dx. Then show that t belongs to d prime of r, and compute t double dash, so second derivative of t. Mod sin x is a nice continuous function, it is locally integrable. Therefore, so solution for every k in R compact, we have mod t phi is less than or equal to integral mod sin x is less than or equal to 1, and so you will get norm phi 1. Okay, so this implies that t is a distribution from the other characterization which we saw. So it is a distribution whose order is 1. Okay, so now we want to compute t double prime. So t double prime acting on phi, we call, is nothing but t acting on phi double prime. So that is equal to integral over r mod sin x phi double dashed x dx. I have just used the definition. So now we will rewrite this. This can be written as, so we want, since we have mod sin x, it is inconvenient, so let us break it up into intervals where sin x has constant sign. So this is summation over all k belonging to the integers of integral k minus 1 pi to k pi of mod sin x phi double dashed x dx. So if you have that k is odd, then it behaves like k equals 1. So because it is 2 pi periodic. Okay, so k equals 1 means 0 to pi. 0 to pi sine is a constant positive function. So we have integral k minus 1 pi to k pi mod sin x phi double dashed x dx is equal to integral k minus 1 pi to k pi sin x phi double dashed x. And now you can integrate this by parts, and therefore you will get equal to, so minus integral k minus 1 pi to k pi of sine will differentiate as cosine x phi dashed x dx, and then there should be boundary terms, but sine will vanish at both these points, so there are no boundary points, and therefore you have this. And now you again integrate by parts once more. So you have minus cos x, so if you transfer the derivative here, you will get plus sin x. So you will get the derivative of minus cos x is sin x, and then there is a minus sign which has to come from the integration by parts. So this is minus k minus 1 pi to k pi of sin x of phi of x dx. And now you will have some boundary terms. So what are the boundary terms? You have to evaluate minus cos x phi of x. Okay. Now at k equals 1, that means 0, cosine is 1, and then here you have cosine is at pi, or an even multiple, odd multiple of pi, you will have minus 1, and therefore you have it is, and there is a minus sign in the front. So you have plus phi of k pi plus phi of k minus 1 pi. Okay, because you take the difference, and the difference will give you yeah, because at k pi it will be minus 1, that will give you a plus, and here it will be this thing with the, because of the minus sign, this becomes again a plus. Okay, so this is what we have. So if k is even, integral k minus 1 pi to k pi mod sin x phi double dashed x dx will be equal to, so now you have minus sign, because from, if k is even, k minus 1 is odd, so this will be like pi to 2 pi, and their sign is negative sign, and therefore you have minus integral sin x phi double dashed x dx from k minus 1 pi to k pi. Okay, and this is equal to, so when you integrate this, you will get integral plus cos x phi dashed x dx k minus 1 pi to k pi, and again sign vanishes at the two end points, and therefore you do not have any boundary terms. And now you again integrate this by parts, you will get, so cos x, the derivative will be minus sin x, but then there is a minus sign coming from the integration by parts, so this will be k minus 1 pi to k pi sin x phi x dx, again plus, so you have cos x at an even pi and an odd pi. Okay, at even pi cosine is 1, and at odd pi it is minus 1, and then you are subtracting, so again it becomes plus 1 again, and therefore you get phi of k pi plus phi of k minus 1 pi. So if you add all these things, so you get at in all the, from, for k odd, where sign is, so k is odd means sign is positive, and you have minus of the sign there, and for k even, this in the interval sign is negative, and you have again, so you have t double dash equal to minus sign mod sin x. Okay, that is the function, C infinity function or locally integrable function against which you have to integrate phi, but then all these boundary terms will there, and each time you will, everything will be repeated twice if you write, because it's summation over k over all integers. So every integer, every of one of these terms will come once in the odd interval, once in the even interval, neighboring interval, and therefore you will get 2 times sigma k in z of, so you are evaluating phi at k pi, and that is nothing but the distribution delta k pi. Okay, so T double dash is this. What does this mean? This means that T double dash, so alternative way of, explicit way of writing this is minus integral mod sin x phi x dx over r, and then plus twice sigma k in z phi of k pi. So, this is how explicitly the definition, this is the same, these two statements are one and the same. Okay. So, we can express a distribution. Whenever we express it, we either give a formula like this, or we just give the in terms of phi, but there should be no derivatives coming in here. So, only it should be an action on phi, which is what we expect in the answer. Okay. Okay. So, this is an important exercise. So, we have seen that locally integrable functions can be made into distributions. Now, even functions which are not locally integrable, by suitable limit processes, sometimes we can convert them into a distribution. So, one such example is 1 by x. 1 by x is not integrable in in a neighborhood of the origin, and therefore, it is not a locally integrable function on R. So, what we are trying to do is, for phi in d of R, define t of equals PV of 1 by x. So, this is called the principal value of 1 by x. This is a technical notation. So, that is where, that is t of phi equals limit epsilon tending to 0 of integral mod x greater than epsilon of phi x by x dx. So, what we are doing is, the only singularity of 1 by x is at the origin. So, we are excluding, puncturing out, cutting out a neighborhood of the origin and integrating this function as though it is 1 by x, and then try to take the limit as epsilon goes to 0. So, and we have to show that this limit exists, so that T phi is well defined and gives you a distribution indeed, and then we will, so the rest of the problem is show that T belongs to d prime of R, and that T is equal to log mod x prime. That means log mod x is a locally integrable function. So, if you take f equals log mod x, then we say that T is equal to Tf dash. Okay, that is the meaning of the statement here. T is equal to, so log mod x is a locally integrable function, which you can check yourself. Okay, so solution. So, let phi belong to d of R, and you look at integral mod x greater than epsilon phi x by x dx. This is equal to integral minus infinity to minus epsilon phi x by x dx plus integral epsilon to plus infinity phi x by x dx. Now, phi has compact support. So, let us say support of phi is contained in minus AA. Okay. So, this, if you make a change of variable x going to minus x in this integral, so you will, so this will become equal to integral epsilon to a of phi x minus phi of minus x by x dx. Okay, so so you can verify that with this elementary change of variable. So let us call psi of x equals phi x minus phi of minus x. So this is equal to integral epsilon to a psi x by x dx. Okay, so now this we can write. So we are going to integrate this by parts. So this will be minus integral epsilon to a of log x. So log of derivative of log x is 1 by x away from the origin, so we have no problems whatsoever. So this is log x, and it is a nice smooth function, differentiable n number of times, and therefore the distribution derivative is the same as classical. Anyway, we are doing just integration by parts. Okay, so and then we have here psi dash of x. So okay, so that means that is phi dash of x plus phi dash of minus x, because there is a minus here, there will be one more when you pick up by the function of function rule dx, and then you have to take the limit, but at the limit a phi, and at a and minus a phi vanishes, and therefore you will have minus psi epsilon log epsilon. So let us let's see what happens to psi epsilon log epsilon when you are taking limit epsilon going to 0 of psi epsilon log epsilon. So we can use the function of function rule, I mean L'Hopital's rule. So you can write this as limit epsilon going to 0 of psi epsilon by 1 over log epsilon. Okay, so infinity by 0 by 0 form, and so this will give you limit epsilon going to 0 of psi dash epsilon minus psi dash epsilon into epsilon log epsilon square. Now this is a bounded function, and this goes to 0. So again limit, so you have to check this again, you can use L'Hopital's rules once more. So epsilon log epsilon square equal to 0, because log epsilon is something which goes much slower than epsilon. So even though it goes to infinity, minus infinity, as epsilon goes to 0, it is much slower than any polynomial, and therefore you have this. Okay, so you can again check this using so this limit is 0. So you can check that again using L'Hopital's rule. So we have T of phi equals minus limit epsilon tending to 0 of epsilon to a log x into phi dash x plus phi dash minus x dx. Okay, so this is what we have. So again you make a change of variable for this integral, y equals minus x, and therefore you will get this is equal to minus limit epsilon tending to 0 of integral epsilon less than mod x less than or equal to a. So this there will be two integrals. The second integral will go from minus a to minus epsilon, and this first integral will be epsilon to a. So I am combining the two and writing it like this. And then if you look at when you change the integral, this will become log of minus x in the negative side. So you will get log mod x phi dash x dx. And now log is a locally integrable function. Phi is a C infinity function with compact support. So, by the absolute continuity of the Lebesgue integral, this is precisely equal to integral over R, okay, of log mod x phi dashed x dx. That is, I have removed a, I have sent to infinity because phi, whether it is over a or over r, it does not matter. So, with a minus sign, of course. So, this is minus log x, and now this is a locally integrable function, and therefore, this is well defined. So, therefore, t is well defined, and in fact, t is equal to log mod x prime, because what is the derivative of the distribution given by log mod x? It is minus log mod x acting on phi dash. So, that is what we have. Okay. 5. So, the many steps here, the changes of integral variable, etc. So, please check every one of them so that you are completely convinced that whatever is written here is correct. So, let phi belong to d of 0 infinity. This omega is 0 infinity, the interval in R. So, I am writing d of 0 infinity. So, this is nothing but that is d of omega, where omega equals the interval 0 infinity. That is the notation. So, define t of phi equals sigma k equals 1 to infinity of phi k of t, the kth derivative acting on 1 over k. Show that t is a distribution and is of infinite order. So, up to now all the examples we have seen, the distributions have been of finite order. So, here is a distribution of infinite order. So, this is an example of a distribution with infinite order. Okay. So, T of phi is, so phi has compact support. Contained in 0 infinity. So, this implies what? Phi k of 1 by k will be 0 for all k sufficiently large. If k is sufficiently large, 1 by k will be outside the support of phi, and so all the function and all its derivatives will vanish. So, this will be 0. So, T phi is a finite sum, and so it is well defined. Also, if phi n goes to 0 in d of 0 infinity, then support of phi n are all contained in a fixed compact set k contained in 0 infinity compact. So, there exists a k naught such that phi n is identically 0 on 0 1 over k naught for all n. That means phi n k 1 by k equal to 0 for all k greater than or equal to k naught. And phi n and all derivatives converge to 0 uniformly on k, and so that will imply that T phi n goes to 0. So, this implies that T is a distribution. So, now let be greater than a greater than 0, and let k be equal to ab, a compact interval. Okay. So, any compact set will be in a compact interval. Then for all support of phi contained in k, for all phi in d0 infinity such that support of phi contained in k, what do we have? Mod of t phi will be less than or equal to c times norm of phi k, where what is the norm phi? It's the derivatives which involve, and what is this k? This k is 1 by k plus 1 is less than a less than or equal to 1 by k, where so it depends on a. Okay, so how many k's are outside this interval will entirely depend on how close a is to 0, and therefore it depends on k. So this implies k depends on capital K. Okay, therefore you have t is of infinite order. Okay, so we will stop here and we will do some more exercises later on after we have covered some more theory. Okay.